Oh, now I'm turned on. Hello and good day, geometry. Here's your explanatory video for math packet number 8, due March 9th. And I'm really only going to focus on the questions that are not also in the algebra packet. If you need more explanation on those, you've probably watched the algebra video already or were here for them in class. So just focus on the geometry only questions here, which we start with here. Mrs. Jones just purchased 36 yards of fencing and wants to fence in a playground area for children. That's nice. The fencing she purchased is of very high quality and can be molded into any shape she desires. She wants to provide the most play space possible. So essentially what we're saying here is she wants to put it into a shape with the largest possible area for students to play in. What shape will give her the most play space, and what is that area? So she's got 36 yards of fencing here. And if you think about, all the different shapes you can mold that into, there's going to be one thing in common. That is the distance around the outside of the shape will always be 36. Is that shape going to be a square? Which, being a square, of course, means it has side lengths of 6 and 6. Okay? I'm sorry, I said that wrong. It'll have side lengths of 9 and 9 because 9 plus 9 plus 9 plus 9 equals 36. The perimeter is going to be 36. And okay, anyway, will it be a rectangle? And there are lots of different ways to make a rectangle with a perimeter of 36. And so you kind of need to think about, well, is it going to be, like a 2 by 16 rectangle here? Okay, or maybe it's going to be a 6 by 10, 8 by 10 rectangle there. If it's going to be a rectangle, what size is going to give you the largest possible area using those 36 yards of fencing? Is it going to be some sort of triangle? Okay, maybe something like that, an equilateral triangle, 12, 12, and 12. What would the area of that shape be? Is it going to be more of a right triangle? Maybe, or you can assign side lengths there. Maybe it's a circle, right? 36 yards of fencing around a circle, that would be the circumference. What would the area of that shape be? If it is maybe even a trapezoid, wouldn't that be fun? A trapezoid-shaped playground area, what would the lengths of that be? So what shape with an outside distance of 36 is going to give you the maximum playing area? That's essentially what this question is asking. And then what is that area going to be if you've got those 36 yards to work with? Next one. That was more geometric in nature. Here we are back to algebra. If home plate is 60 feet, 6 inches from the pitcher's mound, and if the pitcher's release point is 6 feet in front of the mound, how long does it take a fastball thrown at 90 miles per hour to reach home plate? Well, first of all, let's get this out of the way here. The baseball is not traveling 60 feet, 6 inches, right? The pitcher is 6 feet in front of the mound. So really, just so we don't forget, because it's easy to, we're looking at a distance of 54 feet, 6 inches here. Okay, that's how far the baseball is actually traveling. And if we're looking if we're looking at a rate of 90 miles in 1 hour, that's what the rate 90 miles per hour represents, we can convert this into probably inches per second. Might want to go with feet per second. Okay, but we do need to get into some time frame for how long it's going to take to get there. Actually, yeah, I would probably recommend going in feet per second here. So convert 90 miles per hour to the number of feet per second. How many feet does it travel in a second? And then use the distance, 54 feet, 6 inches, which as a decimal, since there are 12 inches in a foot, you'd use 54.5, 6 inches being half a foot there. okay? Feet per second, has to travel 54.5 feet. How long will it take? So a very, very classic conversion algebra type question here, but to start, get that 90 miles per hour down to feet per second and see what you can do with it from there. 5-card challenge, we don't need to discuss. A, because it's in every single packet, and B, because we talked about it already in algebra. Whoa boy, here we go. Calculate the percentage of the figure that is shaded. Show all work, including every calculation. The figure is a square, and all circles or parts of circles are congruent. So let's start with the area of the entire figure, okay? The one measurement we are given here is this 5 centimeters, and that represents the diameter of this circle. And because it says that all circles are congruent, then all circles or parts of circles here will have the same diameter, which means that the radius, which is here, is going to be half of that, or 2.5. This radius here will also be 2.5. So the overall side length of the square is 10, right? And that should help you calculate the total area of the figure. To get the shaded region, though, there are a couple different ways you could look at it, okay? Probably the way I would attack this is I would go with the method of taking that total area and subtracting the white section, subtracting the parts that we don't want. So we're going to look at how many circles we have total here, right? And then start subtracting whole circles or halves of circles or quarter circles, however you want to combine them to make it work for you to get the area of the shaded section, okay? That does throw a little bit of a curveball at you in that, you know, we've got a shaded area here, this purple diamond-like figure inside of a circle, but think about how you can account for that, okay? And here's my hint. If you can work this down to just find the area of one of these shaded curved diamond pieces, know that there are 5 of them total. And so if you can figure out the area of one of them, you can easily get to the area of 5 of them since they are all the same size. So I'm going to leave you with that for this one. A little bit that needs to be done on your own, but again, I'm more than happy to help you, especially if you turn in early for me to check over. Next one, the Swedish Flag. We've already talked about this in algebra. Your extra task here is to write an expression, 2 of them in total, representing the number of blue blocks and total blocks in the nth figure. And this is one of your expressions is going to be the same thing you had in packet 7 with the total blocks, right? Because that packet also dealt with just making squares. So the total blocks, as we go through this column here, figure 1 has 1 total block, then 9, 25, 49, 81, 121, 225, and 289, I believe. Did I miss one in there? Oh, yes, I did. Whoops. Too bad I don't know how to edit these things. 169 and then 225. Okay, and what we noticed here was that these all being the odd perfect squares, to get to 1, we take 1 squared, then 3 squared, 5 squared, 7 squared, 9 squared, and so on and so forth. Okay, so as far as writing the expression goes, remember we can think of this as kind of like a function table to where we have the figure number and the total blocks as our input and our output. But instead of using 1, 9, 25, 49, 81, 121 as our outputs, we're going to use these numbers here because they're a little bit smaller. And whenever we get that number, our final step is always just squaring it. So if you make a function table, we'll call it figure number and total blocks, and you start this out in figure 1, there's one total block. In figure 2, there are 9, but we're going to focus more on getting that 3. In figure 3, there are 25, but we're going to focus more on getting that 5. In figure 4, there are 49, but we're going to focus more on getting that 7. Because however you get that expression that you come up with to get from 1 to 1, 2 to 3, 3 to 5, 4 to 7, whatever it is, you're just squaring it. Okay? So we can kind of ignore the power of 2 for now to get to that intermediate number and then just square it every single time to get to our actual total block tally. Okay? And then from that, you can think about it as the total blocks, and you're just subtracting the number of yellow blocks to get to blue. That could be a route you go and find the pattern for that. You could do something similar because, of course, the blue blocks, we started with 0, and then 4, and then 16, and then 36, 64, 100, 144, 196. These numbers were the even perfect squares. Right? So again, when you make your function table, you're going to be looking for how do I get from the figure number to these numbers here. Okay? And you could go that route. All right? So, need extra help? Please do come and ask. That should get the gears churning, especially from packet 7, for how to write these expressions for the bottom of the table. Then we get to this one, which we talked about in algebra. We talked about this one in algebra. You need to do 5 of the 7. So you have to do one of them that involves pi, either the cylinder, the cone, or the sphere. I don't know how well it shows up on your packet, but remember this says the volume is approximately 904. Okay, since you're using pi, you aren't going to get a volume of exactly 904, but maybe you come up with a volume of 903.7. That's about 904. Maybe you get 904.9. That's about 904. 901 is too far away. Okay, 906 is too far away. All right, you want to get as close as you can here, okay, to 904, filling in those values. Our math exploration, also talking about Fibonacci. Are we doing Fibonacci? No, Pascal's triangle. I thought this was. Oh, here we go. Okay, so we mentioned Fibonacci here. So back to Pascal's triangle is another mathematical pattern we've talked about this year. Some of the things we've already talked about or have mentioned about Pascal's triangle. The sum of the numbers in a row is twice the sum of the row above it. So for example, if we add up the numbers in this row here, 1 plus 5 plus 10 plus 10 plus 5 plus 1, that equals 32. The sum of the numbers above it, 1 plus 4 plus 6 plus 4 plus 1 equals 16. Right? The sum of a row is double the sum of the one above it. The shallow diagonals sum to be the Fibonacci numbers. In the math packet, the algebra one, we are talking about Fibonacci there. And what this means, the sum of the shallow diagonals, is if we have just like 1 coming through here, and then 1, 1. Oh, sorry, skipped 1. Right? And then 1 plus 1 is 2. Our next Fibonacci number is 3, which is 1 plus 2 plus 1, or 2 plus 1 there. And then the next Fibonacci number is 5, which is 3 plus 4 plus, wait, I'm not drawing these shallow diagonals correctly. Hold on. I'm not drawing those in correctly. Let me just ponder this here for a second. So we got 1, 1, and 1 again, and then they come through like, no, yeah. 1 plus 1 is 2, and then 2 plus 1 is 3, and then 1 plus 3 plus, there it is, 1 is 5, and then 1 plus 3 plus 4 plus 1 is, not counting that first one, 8. Yeah, the shell diagonals kind of take it at the, they are diagonals that are here and then here, and only the numbers that actually pass through are the ones that you count. I kind of botched that explanation, but sorry about that. They've got patterns in the multiples of 2, 3, 4, and 5, and like you did do in an algebra packet, any number that you start with, there are exactly that unique paths to get to the top of the triangle. In a previous packet, you started at 21, and you look at all the different ways. There are 21 unique ways to get to the top of the triangle. But today, we're going to look at alternatively adding and subtracting the numbers in a row to equal 0. For example, row 4 looks like 1 minus 4 plus 6 minus 4 plus 1 equals 0. Right? Here's row 4. 1 minus 4 plus 6 minus 4 plus 1 is going to equal 0. We can also make that first one negative and do the same thing. Negative 1 plus 4 minus 6 plus 4 minus 1 equals 0. Okay? So we're going to try with row 5, beginning with 1. Fill in the blanks and keep a running total by writing each sum in the sequence on the line below the equation. So beginning in row 5 here, which is this row here, we got 1, 5, 10, 10, 5, and 1. So 1, 5, 10, 10, 5, and 1. Okay? So when I say keep a running total, we're going to take 1 minus 5, which is negative 4, then add 10, that brings us to positive 6, then subtract 10, back to negative 4, add 5, positive 1, minus 1 equals 0. Okay? You're going to be doing that with row 8. You're going to be beginning with negative 1. Okay? So this is going to be negative 1, and then plus 8, and then minus 28, and then plus 56, and so on and so forth there, keeping that running total. And then row 10, which is here, beginning with a positive 1. So 1 minus 10 plus 45 minus 120, etc. Again, keeping that running total. Okay? And I don't ask you to do this on the page itself, but think about why this happens. What about Pascal's triangle ensures that this will happen, whether or not you start positive or negative? What's going on here? Okay? What's going on here? And I think that about wraps it up. We have our probability tree here, which we did talk about in algebra. Your question for this, a bag contains a red chip, a blue chip, and a green chip, so the same starting situation. A chip is randomly chosen, put back in the bag, and a second chip is randomly chosen. Using a tree diagram, what is the probability of choosing a red or blue chip on either drop? So your probability tree is going to look the same as it does for algebra as far as what all of your possible options are, your possible outcomes. But the successful outcomes are going to be different. In the first one, it's just the probability of choosing a red chip on either draw. In this one, it's choosing a red or blue chip. And lastly, we have our Polyaminos. You've got 12 of them. Where they appear in the figure, they are not flipped or turned or rotated or anything. All of them appear exactly once, and you need to identify where they are. So that's math packet number 8. I hope you enjoy it. It is due March 9th, as long as the other packets we have from this try. Don't forget, you can turn it in early, and my boss is calling me, so I gotta go. Have a nice day. So long.